Today we will learn about graphical analysis.
If you stare at a live feed of raw process data, a sprawling spreadsheet logging every temperature fluctuation on a factory floor or every timestamp in a customer service queue, you will learn absolutely nothing. The numbers in their raw state are chaotic and inherently illegible. To extract actionable intelligence from this noise, we have to translate these numbers into geometry. This reveals the hidden signatures of the operation, such as the overall trend, the frequency of specific events, and the overall distribution shape of the data. This translation is an exact mathematical process. It requires taking specific data types and applying rigid geometric rules to expose underlying patterns. Look at this source image, which shows raw food ingredients sitting alongside structured data reports. Whether you are conducting food quality control or nutrient analysis, you need these visual tools to confirm that physical materials match strict numerical standards. To execute this graphical analysis at scale, engineers rely on specialized software instruments. Microsoft Excel handles baseline reporting, while programs like Minitab process heavier statistical modeling. We are going to deconstruct the three core graphical instruments used in this field: dot plots, scatter plots, and histograms. Effective visualization requires matching the specific behavior you want to measure with the exact mathematical geometry designed to expose it. Without applying the correct geometric tool, raw numbers remain meaningless, making it impossible to monitor or improve your process parameters. The dot plot is the simplest architectural form we use. We deploy it specifically to map small sets of numerical, discrete data that can be counted in distinct whole numbers. The construction relies on a single dimension. A horizontal number line is established as the primary axis, representing the range of possible values. The rule for data entry is strictly 1-to-1. You place a single dot above the corresponding number on the line each time that specific value occurs in your dataset. This dot plot maps the number of books read by students. When a value repeats, like the 4 students who each read 1 book, the dots are stacked vertically to map the exact frequency of that outcome. This vertical stacking instantly exposes the distribution of a small sample. Within seconds, you can spot where the majority of the data clusters and easily identify any extreme outliers sitting far away from the main grouping. While highly efficient for isolated counts, dot plots are bound to a single dimension. Because of this, they cannot evaluate how one shifting variable might influence another. To measure dependencies, we expand the scope to 2 dimensions using scatter plots. This allows us to track values across 2 different attributes at the exact same time. This scatter plot demonstrates the 2-dimensional architecture. The x-axis tracks the independent variable, books read, while the y-axis tracks the dependent variable, total pages read. The independent variable is the condition you measure directly, while the dependent variable is the outcome you are tracking. Every singular dot in this matrix represents a unique intersection of those 2 variables for one specific data point. In food quality control, an engineer maps cooking temperature on the x-axis against moisture loss on the y-axis to optimize a baking process. For nutrient analysis, they plot the fat content of different food samples against their respective calorie counts to verify nutritional consistency across batches. By exposing these specific intersections, scatter plots serve as a primary diagnostic tool. They prove correlations, allowing engineers to verify exactly how a change in one parameter alters the outcome of another. Both dot and scatter plots break down when confronted with continuous data. If your data can be broken into infinite fractions, like time, weight, or distance, and rarely repeats exact values, individual plotting fails. Consider a retail manager who records 27 customer wait times, measured to the exact second. The data points range from 12 seconds to 65 seconds. If we attempt a dot plot here, the high variation in seconds spreads the dots completely thin across the number line. Because there are almost no repeating exact seconds, no vertical frequency stacks form. The pattern remains hidden. To analyze this continuous data, we must compress the individual points into logical ranges. This requires the mathematical construction of a histogram. We begin the histogram derivation by establishing absolute boundaries. We take the maximum value, 65, and subtract the minimum value, 12, calculating a total range of 53. Next, we decide the number of class intervals, or bins. For our dataset of 27, a target of 6 bins provides optimal compression. We divide our range of 53 by 6, yielding 8.83. We round the width up to the nearest whole number, exactly 9. Starting from our minimum value of 12, we add the width of 9, creating our first interval, 12 to 20.9. We sequentially define the remaining 5 intervals based on that uniform width of 9, ending our 6th bin at 65.9 to encompass our absolute maximum value. With boundary set, we determine the frequency height by counting how many wait times fall within each range. Our final frequency counts fall sequentially into the bins as 7, 5, 6, 5, 2, and 2. These exact calculations successfully compress chaotic variables into a structured matrix that is ready for physical projection. We set up the physical graph by drawing a horizontal x-axis mapped with our 6-bin intervals, and a vertical y-axis scaled from 0 to 10 to accommodate our highest frequency count. For each interval, we extrude a rectangular bar upward from the x-axis boundaries until its height matches the precise frequency count of the data points inside that specific bin. Notice the crucial structural difference of the histogram. Unlike a standard bar chart, there are absolutely no gaps between the bars. We complete the graph by labeling the axes. The x-axis identifies the variable we are measuring, wait time in seconds, and the y-axis is labeled as frequency. This continuous architecture is necessary because the data itself is continuous. The boundaries of one bin flow immediately into the next without interruption. The adjacent bars visually confirm that the process operates on an unbroken spectrum, giving us an accurate scale model of the total distribution. Once constructed, our focus shifts from mathematical derivation to interpretation. The macro shape of the final histogram directly reveals the underlying behavior of the process. This source image illustrates standard histogram profiles. On the left is the normal distribution, a symmetrical, bell-shaped curve. This indicates a highly stable process that is centralized consistently around a specific mean. When a process deviates from this symmetry, we measure it through skewness. Skewness is a metric in descriptive statistics that characterizes the exact asymmetry of a data distribution, showing if the data leans heavily to the left or right of the mean. We also measure kurtosis. Kurtosis is a secondary metric that determines the heaviness and extremity of the distribution tails, revealing if the process is prone to extreme outliers. In practice, evaluating the shape of these distributions is how you monitor the weight of packaged food items for consistency, assess microbial counts to determine product shelf life, or optimize service efficiency based on actual customer wait times. Selecting the correct graphical instrument takes an illegible list of raw variables and transforms it into a precise visual diagnostic model, providing the exact clarity required for rigorous quality control.
Disclaimer: Artificial intelligence, AI, was used in the development of selected instructional materials in this lesson. The use of AI is intended to enhance clarity, visualization, and learning engagement, while all academic content has been reviewed and guided by the instructor.